In the previous session, we discussed about the three-dimensional state of stress. In the biaxial state of stress, we learned how to transform the given stress system into a particular plane. We know that the value of stress is going to be different as the plane changes. So in this session, we are going to discuss about the Cauchy's stress transformation, where we will discuss in detail about the stress transformation in 3 dimension. Let us consider a cuboidal element with all the stress components. We have the normal components sigma xx, sigma yy and sigma zz. Along with that, we have all the shear components. Shear components can be notated using the letter tau as well as sigma, but the indices are different here. So the different indices indicates the shear stress. So these are two different methods to notate shear stress. Please don't get confused with this naming. Now, what I am interested to find is to find the stress at a particular plane in 3 dimension. Let us consider a plane like this. A plane which is inclined at some particular angle theta x, theta y and theta z with the x, y and z axis. And the enlarged view of this particular plane is given over here. So now we have to learn how to transform the given external stresses into this particular plane A, B, C. We already learned that we cannot directly transform stress, or we cannot directly resolve the stress into a particular direction. In order to resolve, we have to first convert these stresses into forces. So it is very simple to convert this stress system into force. It is by multiplying it with the corresponding normal area. So we are now going to find out the area of the plane AOC, COB and AOB. We assume that the area of the plane ABC as capital A. Then this particular plane makes an angle of theta x with the x axis, theta y with the y axis and theta z with the z axis. And if we resolve this particular area into AOC, the value is going to be A cos theta x. Similar manner, if you resolve the area ABC to the yz plane, it is going to be cos theta y. And if we are going to resolve this into xy plane, it is going to be cos theta z. So this cos theta x, cos theta y and cos theta z are called the direction cosines, and they are notated using nx, ny and nz. So anx means the area AOC, any means the area COY, anz means the area AOB. So right now we have all the forces, all the areas associated with this particular tetrahedron. Now we are going to transform these forces into this particular plane. Now in order to find the stresses in this particular plane ABC, what we are going to do is to resolve these forces which are acting on different planes to the particular plane ABC, and after that we are going to resolve it into the normal direction. So in order to do that, we have to define a new axis system here. That means let us consider this as the x dash axis, y dash axis and this as the z dash axis. These are the x, y, z of this particular new plane A, B and C. They are not the same as that of x, y, z. They are something different. This is x dash, y dash and z dash. Now what we are going to do is we have to transfer the forces on these planes to the new x dash, y dash, z dash axis. Now let us look into that. See, if we consider the equilibrium in the x direction, we have to consider the body forces also. So we assume that the body forces are Bx, By and Bz, which are nothing but the body forces per unit volume. So in order to get the force, we have to multiply the body forces with the volume of that particular tetrahedron, which is nothing but 1/3 of A into H. So when you consider the equilibrium in the x direction, one force is sigma x into A into Nx. So A into Nx gives the area of that particular phase where sigma x acts, and tau xy into A ny gives the force in the x direction. Next force in the x direction is tau xz, and whose area is Anz. So minus the body force, equal to what? The force in the Tx, x direction, this force into area on which it acts. That is what it's given here. So when we cancel out all the similar terms, because all the terms that is written over here is nothing but force terms, there is no stress term. So when you cancel out all these area, and if we consider that the body force is negligible or is nil, then what the terms that is going to left with is Tx is equal to sigma x nx plus sigma xy, tau xy ny plus tau xz nz. So in a similar manner, if you write down the equilibrium equation in the y direction as well as the xz direction, you will end up with equations like this. These three equations are called as the Cauchy's stress equation. These are called as the Cauchy's stress equation. So if we closely observe these three equations, it can be easily denoted in a matrix form like this. So Tx, Ty, Tz are the stresses on the plane ABC in the x dash, y dash, z dash direction, and which is nothing but the three-dimensional stress matrix into the direction cosine column matrix. So the first row into the column gives Tx value, this equation. The second row into this column gives the Ty value, this equation, and the third row into this column value give Tz. This is how we denote it in the matrix form. Now what we have obtained is the stresses in the x dash direction, y dash direction and z dash direction. Now our aim is to find out the stresses acting normal to this plane. So if you want to find out the normal, it's very simple, because right now we have sigma x dash, sigma y dash and sigma z dash, and we know that this angle and this angle are nothing but theta x, theta y and theta z. So it's very simple to find out the value which is acting normal to this plane. It is just by resolving this sigma y dash, sigma x dash and sigma z dash to this particular normal, simply multiplying it with the cosine values. So it is going to be nothing but the normal stress acting on the plane ABC is nothing but Tx into cos theta x, Ty into cos theta y plus Tz into cos theta z, which is nothing but Nx, Ny and Nz. And we know how to find out the resultant stress if we have three values. It's by taking the square, adding it up and taking the root. So the value of the resultant is nothing but Tx square plus Ty square plus Tz square. This Tx, Ty, Tz are the stresses in the x dash, y dash, z dash direction of the plane ABC. It's very simple. This is a fundamental equation that we use in the equilibrium or the static conditions. Resultant is equal to the root of fx square plus fy square plus fz square. It's a very commonly used set of equation. And now we have to relate this normal stress, resultant stress and the shear stress. So in order to understand that, we will do it like this. So this is nothing but the normal stress acting on the plane that when we have find it out here. Sigma n is equal to nx tx plus ny ty plus nz tz. This is the normal stress. And we have the shear stress acting on that normal plane which is nothing but tau n. So definitely this tau n and sigma n are mutually perpendicular. So when we represent it by a vector, this is going to be what? The shear stress, and this has to be the resultant. So right now we have calculated sigma n and we have the resultant. If we know these two values, we can easily find out the shear value. It is by resultant square is equal to altitude base square plus altitude square. That's all. Simple trigonometric relation. So using this relation, the unknown value is going to be tau n. So this can easily be found out. So this is how we calculate the normal and shear stresses acting on a plane. In simple words, we can say that multiplying the three-dimensional state of stress with the cosine matrix or cosine matrix will give you the stress in the x dash, y dash, z dash direction. Again, if we multiply these stresses with the cosines, it is going to fetch you the normal stress. And when we square it up, add these together and take the root, we will get the resultant stress. And finally, the resultant normal and shear can be found using the simple trigonometric relation. This is how we find the stresses or transform the stresses in three dimension. This is how we found these stresses on a particular plane. Now there are a different set of transformation available if we change the coordinate system. So right now the coordinate system is x, y and z, and if you want to find out the stresses in a different coordinate system, then the system of equation that we have to derive is a bit more complex, and that is not covered here. Anyway, the stress transformation can be done in different methods in the three dimension. So that's all for the Cauchy's stress transformation. Kindly go through, write down and practice it. It's very easy for you to understand. Use the basic static principles to understand the stress transformation in three dimension. Thank you.